Okie doke. I suppose we'll get going. I sent out an email that no one read because I know what students are like and nobody will read my emails. That's fine. I mentioned that doing like 2 full days of lecturing was probably a mistake. I probably shouldn't have done that. Should have stuck to the thing I always do. So I've crammed too much math into it. So today is a light day where it's just going to be, I'm going to go over some stuff and then I'm probably going to review it again on Monday. So it's going to be short, and then you have a quiz that I said originally I was going to, cover how to solve systems of equations the good way, and then I was going to put on the quiz, and then I was looking at it, I was like, this is like too much. So I was like, no, well, I looked at the calendar and I was like, oh, we have time for me to not care about that. I don't know why I was rushing. So anyway, so short day. But last class, the important things we talked about were more properties of vectors and dot products specifically. So this is something you can do on 2 vectors, and it will give you a number, not another vector. So it's not like multiplication. We also talked about length, which uses the dot product, which is the square root of a vector dotted with itself. And then distance was just the length of u minus v, and I gave like a picture of that. And then we started talking about systems of equations. And that's what we're going to spend the next little while on, probably next week. But I do want to at least start talking about some of the matrix stuff so that we can have it and we don't have to worry too much about it. But this stuff I'm about to talk about is not on the quiz, so don't pack it in there too hard. So remember, a system of equations is just a collection of equations in some number of variables. So like 2x plus 3y is equal to 5, and 2y minus 3z is equal to 2, right? This taken together is a system of equations, linear equations specifically, but everything we're going to talk about is linear, so we don't bother saying it. So something like this, right? It's just equations. And at the end of the day, on a Monday, I showed how the classic technique of solving these types of things, where it's like isolate for one variable and then use it to eliminate the other variables and then go backwards, and it's really tedious and messy. So our goal is to do better than that. So methods for solving equations. I mostly want to talk about matrices real quick. And then we'll do the quiz on this short day. So what is a matrix? It's something that we're going to need to basically discuss all of this stuff. So a matrix is a rectangular array of numbers. Array of numbers. The numbers inside of it are called entries. And the notation we use for a matrix would be, we usually use capital letters, and it's just something like this. Right? It's just a rectangle. This is a square, but like it's a rectangular array of numbers. So this matrix above here has size. We write 3 by 3 because there are 3 rows, 3 columns, right? So we say it's 3 by 3. Three rows and 3 columns. So this is the number of rows, and this is number of columns. Already sort of looking at this, you can see how it would be related to programming and stuff, right? Because we've got, we can envision just a row of a matrix or just any kind of row as an array, right? It's just a list of numbers. So then you've got a list of numbers here, essentially, which is a two-dimensional array. So something that's like this indexed twice will give you a matrix, right? Because you could say this is rows and this is columns. So in this sort of notation here, this entry would be row 2 and column 3. So if we were, using indexing at 0, it would be like that, right? Entry, this is row 0, 1, 2, column 0, 1, 2. So row 1, column 2, right? So that's why this is a useful object, right? Because we work with them pretty often in programming. They're just useful to deal with, because there's a lot of nice properties about matrices, which is a good tool to have in your toolbox. Now, the reason why we care about this is because we can very easily associate one of these with a system of equations. And this is so because I crammed a bunch of messy math into your head, normally I would talk about the abstract definition here, but we're just going to jump into an example to show you what I mean, and then I'll explain this another day. But we can very easily get a matrix from this system as an example. So we can get a matrix or set of matrices, because there's a couple of them, from a system. So there's kind of a natural one here, I would say, right? We've got this rectangular array of numbers. And if we just so we're going to put the plus 0z here, 0x. We could look at this and there is kind of a rectangular grid of numbers here, right? We just have the variables coming along for the ride, right? So we could say, call A this, or we just take the coefficients here. So this, like that, 2, 3, 0, 0, 2, minus 3, like this, right? So you can see that direct correlation here, right? So this thing is called the coefficient matrix. And we also have this right here as another thing. It's sort of on the other side of the equal sign, and we're sort of splitting all of this up for a reason that will become more obvious later. So this is a vector, which we would call the vector of constants, or column of constants. And I'm saying, well, this is also a matrix, because a matrix is a rectangular array of numbers. Well, it's not a rectangle, right? It's got 2 rows and 1 column, but it's still a rectangular array of numbers. We call this a vector, generally speaking, but vectors are matrices. They're just very specific cases of them. Vectors are matrices. Okay, but what we often like to do is sort of combine these two into one thing, which we call the augmented matrix. And the notation we'll use for it generally is something like this. So we'll put A and then a slash through it, and B, and we're just going to combine these two matrices. So we're going to take this thing here, 2, 3, 0, 0, 2, minus 3, and put a slash through it, 5, 2. So this is called the augmented matrix. And this is what we're going to end up using to solve systems of equations. Because if we take a look at this, this is just a nicer looking version of that set of equations we had written down, right? It's just, we kind of tuck the variables away and, we're simplifying the notation a lot. Now, there are things that we could do to matrices, specifically, that will be very helpful to us. So there are some things, operations specifically, we can perform on matrices. In fact, there's actually a lot, but the ones that we're interested in right now are what we can do to these rows. So the first thing we can do is we can swap two rows around, right? And let's just think about it, right? This here represented this. 2x plus 3y equals 5. 2y minus 3z equal 2, right? Does it matter if I write this or write this equation first? Like, no, right? I mean, yeah.
Does that work for n rows?
Yeah. So you can swap well, so what's called the elementary row operation only swaps two rows around, but as long as you keep track of it, you can move them around however you want. Yeah. So like you could, if there were 3 here, you could just rearrange them however you want, and that's fine. Because these represent equations, right? And it doesn't matter what order we write them in, right? Just equations. So who cares how we write them? So that makes sense. So we can swap 2 rows around or more rows if we want. So what we can do, we can also multiply a row by a non-zero constant. And this kind of goes back to equation stuff. If we think about it, if I multiply this equation here by something that's not 0, it doesn't really affect anything because I can just divide by that number again, right? And go back to where I started. So it doesn't change the solutions. If we think about it, you have an equation that looks like this, 2x equals 2. We can multiply this by whatever we want, and the solution will still be the same, right? X is 1 is the solution to this. So that if I write it 5x equals 5, it doesn't matter, right? It's still telling me the same information. So that's what this is saying, right? We can multiply an equation by any number. So that means we can multiply a row by any number. And this is the one that's a bit weirder. It turns out this is true for equations too. But if you don't remember it, it's okay. So we can add a multiple of a row to any other row. So it turns out this is true for equations too. You can actually you could create a new system of equations by taking this equation and adding it to this one. And that will give you a new system of equations, but they still have the same solution, it turns out. So related to equations, that's why we can do it. But these operations here aren't actually mentioning anything about the equations, right? These are just true on matrices in general. It doesn't matter if there's equations or not. These are what are called elementary row operations, and we can just do them. So some examples here. And then I'll write down one definition, and then we'll leave it. So what we can do is, let's say we have this matrix, 2, 3, 7, 5, 3 minus 6. So we could say swap row 1 with row 2. So this is the notation we like to use to indicate this is what we've done. Just so, well, for one, if you're submitting something to me, it makes it easier for me to see what you did. But also for you, it makes it easier for you to see what you did, right? If you just use some kind of notation to say, hey, I just swapped row 1 and row 2, you don't have to, look at it and go, okay, what did I do? Right? I mean, we could look at this and say, okay, yeah, I swapped. Like just peeking at this, you can be like, oh, those are swapped. But if it's more complex, it's less obvious what you did, right? So it's nice to just write down your steps. Okay, another example. So we've got this matrix here. We can multiply any row by a non-zero number. So let's do 2 row 1. So what does that do? We just multiply row 1 by 2. Right? Straightforward. Okay, another example, which I'm running out of space. We'll do this over here. I got this matrix, 2, 6, minus 1, 0, 4, 7, minus 1, 3, 1. And we do row 3 becomes row 3 minus 2 row 2. So this is just the notation I like to use. There's lots of different ways you could do it. You could say equals or whatever you want. But this is just saying row 3 is going to become row 3 minus 2 row 2, right? So this is something you could do in your head, or you can write it down on the side, whatever you want. There's lots of different ways to do it. But row 1 and 2 are not changing, right? Row 3 is the one that's changing. So what do? We just minus 2 times this from this. So minus 2 times 0 to that is minus 1. Minus 2 times this is minus 8 to this is minus 5. Minus 2 times this is minus 6 to this is minus 5. Okay. Wait, did I do that right? I didn't even end up writing down the same matrix, so whatever. Yeah, I did it right, I think. But my hesitancy there, my doubt, is I would say a warning, but also not a warning, that once you start doing these enough, like you go through like 10 different steps, and all of the operations are like this, where you're just like adding and subtracting small numbers from each other, which like most of us can do, right? It turns out it's really easy when you do that like 20 times to screw it up just a little bit, right? Like here, you just do, so, you know, you're doing minus 2 times all of these and then adding it to this. So maybe you just forgot the minus one time. So you did 6 plus 1 and you got 7 or something. That throws everything off. It completely ruins everything. But in terms of the question and understanding and that sort of thing, it's not that bad, right? It's just you made an arithmetic error in your head or whatever. It happens. It's not a big deal. So when it comes to actually doing exercises, don't stress that too much. I'm more interested in your understanding and going through the motions and doing the steps and whatnot than I am about you saying, hey, the answer is wrong. Okay, well, did you do the row reduction correctly, which is what we're going to end up talking about on Monday? Yes? Okay, then we're good. Okay, so the last definition I'm going to talk about is what's called row echelon form, which is a big scary math word for something that is just a shape of matrices. So a matrix is in row echelon form. We'll often abbreviate this as REF. If it basically has a specific shape, so any rows entirely consisting of zeros are at the bottom. So we look at something like this. I'm going to write down an example of one. So there we go. We got there's a row of zeros that's at the bottom. That's good. We want that. That's one of the conditions. The other one is a mouthful to write down. So the first non-zero entry is it a row or column? From the left in any row has zeros below it. let's say to the left and below. So actually the terminology I use in the notes is in a column to the left of any leading entries below it, and that's a mouthful. What this is essentially saying is if you look at any row and you say, okay, let me find the first non-zero thing in that row, to the left of it is all zeros, obviously, because we select the first non-zero thing in the row, and then below it is zeros. So we take a look at this thing, this row. This is the first non-zero entry. There's nothing to the left of it, so we're good. Below it, all zeros. Then we do this row. Okay, that's the first non-zero entry. To the left of it, there's a zero, good. Below it, all zeros, right, in the column. And then we go to this one, there's no non-zero thing, so we're done, right? What this actually ends up looking like is there's a general shape here. You get sort of a staircase shape surrounding all of your numbers, and then everything below that staircase is all zero, right? That's what it ends up looking like. So we'll do a bunch of examples because this ends up being an important concept. Actually, there's something even better we can do. We can insist that there's zeros below and above these. And that ends up being pretty helpful. So these entries are called leading entries. They end up being important. So we refer to them a lot. Okay, so hopefully after doing a messy equation solve on Monday, we're talking about this, and it seems a little nicer, right? They're rectangular grids of numbers, and ultimately what we're going to do is we're going to say, hey, we can perform these operations that we just talked about, swapping rows, multiplying a row by a number, or adding a multiple of a row to another row to get any matrix to have this shape, right? And it turns out that will let us solve equations very easily, right? Because these all represent, this still represents an equation, right? So it works out really nice. Okay, like I said, I wanted to do a short thing. I didn't want to go too far into it. Already, that's probably more than I really wanted to talk about, but I just wanted to do something that wasn't awful. So